Assalamu alaikum wa rahmatullahi wa barakatuh. Peace be upon you all and welcome to the channel. In this video we will discuss the different types of linked lists that we alluded to previously, which are the standard and circular linked lists, as well as explain the differences between a singly linked list and a doubly linked list. But before we begin, Bismillah ar-Rahman ar-Rahim, Alhamdulillah Rabbil Alameen. والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه ومن تبعهم بإحسان إلى يوم الدين وارض اللهم عنا معهم أجمعين اللهم آمين. اللهم صل على محمد وعلى آل محمد كما صليت على إبراهيم وعلى آل إبراهيم وبارك على محمد وعلى آل محمد كما باركت على إبراهيم وعلى آل إبراهيم في العالمين إنك حميد مجيد. We begin in the name of Allah, the most merciful in this life and in the hereafter. We thank Him for all of His blessings that He has bestowed upon us, for they are innumerable. And we pray that we follow in the footsteps of Prophet Muhammad, peace be upon him, and his fellow companions. Amen. We also ask for prayers and blessings to be bestowed upon Prophet Muhammad, peace be upon him, and his followers as they were bestowed upon Prophet Ibrahim, peace be upon him, and his followers. To reiterate what we mentioned previously, we have two main types for a linked list, a standard linked list and a circular linked list. And for each of these main types, we have two subtypes, a singly linked list and a doubly linked list. To try and present this lecture in an understandable fashion, we will discuss what singly and doubly mean. Then, at the end, we will explain what a circular and standard mean. So, let us discuss the structure by which items or elements are organized in memory within a linked list. So, we have discussed previously that list refers to a dynamic collection that can shrink and grow based on its size, and it is part of the collections framework, as we mentioned, but also it stores elements in the sequential order, which is provided by the developer. And we mentioned that linked here refers to the fact that the memory blocks associated with the elements that are stored within a linked list are discontiguous or uncontiguous. The borders of the memory blocks do not necessarily touch one another. They are not contextual or conterminous. As a result, we have three different scenarios by which data can be stored or arranged within a linked list. Firstly, let us design an object of the linked list class is equal to new linked list, like so. And remember, anything related to the collections framework is a generic class, so we must pass in the data type of the elements we will store as a parameter here. Now, what is the sequential order of the elements that I wish to store in this list? We will say I wish to store 1, 3, 4, 7, and 9 in that list. Oh, sorry, I have to take this. I will be right back. Apologies for that, I have returned. Okay, so let us say this is the sequential order. Just to clarify what is meant by the sequential order, when we add these numbers to the list here, I will add them in this particular order. And yes, the linked list object or class has the add method that functions in a similar fashion to the ArrayList add method. So it will be like so: 1, then 3, then 4, then 7, and finally we have 9, like so. This is the sequential order. It is the order I have designated. It does not refer to the natural order or the proper ascending order. And to avoid causing this confusion, what I will do is I will put the 7 before the 1 here, just to emphasize that the sequential order is unrelated to the natural order or sorting. Sorting will be covered later, بإذن and God willing, especially comparable and comparator interfaces. So let us say this is the sequential order of the numbers or integers that I wish to add to the list. Here are the 3 possible scenarios. They are not the only scenarios, but these 3 can have variations, creating multiple scenarios, but they can be summarized or grouped into 3 main scenarios. If this is the memory where the numbers will be stored, it does not really matter if it is the stack or the heap, because we have discussed how memory is actually stored there. But because this is an object, it will obviously be stored in the stack, in the heap. And a reference to that will be stored in the stack, which is the pointer, as we have mentioned previously. Like so. Here we go. And I will erase these. The first scenario will be, or will involve, having the elements stored contiguously. This does not, however, affect how a linked list functions. Even if they are stored contiguously, the linked list stores its elements in a particular fashion, which is quite different from an array list. So this could be a possible scenario. Again, you do not control how the linked list object will store the information within memory. This could be a possible scenario, that the memory blocks will be contiguous in a similar fashion to an array list. And I say similar because linked lists do not store the value of the element only within a memory block. There are additional information. Another scenario would involve, or would have this structure, for example. Some of the memory blocks will be contiguous while others will have gaps between them, but they are stored in the same sequential order. That is another potential scenario. The third scenario would be that you can think of it as a combination of the first 2 scenarios. We can rearrange it, place it here like so. That they would not be contiguous, but also they will not be stored in the same sequential order. So these are the 3 main possible scenarios by which a linked list stores the data within it. We will use either the second or the third scenario for our example to define a singly and a doubly linked list. I will actually use this one, this third scenario here, but I need the space for what is to come. So let us say, even though this is the sequential order, this is how the data were stored. The question is, how would a linked list know which element it should retrieve for its object? For example, the data stored here, here, and here, and there as well, I missed this one, could be a reference to another object. For example, we could create another object. I will use the green color here. Let us say string name is equal to Salim the first. I forgot his epithet. He has a title which I believe means the storm, if I recall correctly, but I do not remember the name of, I do not remember the epithet or the title. If you know, please share in the comments below. I mean, I do know the name, I just do not remember it right now, unfortunately. This is, of course, one of the great Ottoman sultans, or emperors, however you wish to define them, who ended the threat of the Shias in the how do I say the name in English? Well, they are called the Safawiya dynasty. Basically, it was a renegade group that started forming the Shia religion in the region of Persia or Iran now, and he ended the threat, thankfully, which is why he is despised, of course. But anyways, this object will be stored here, for example, or in this block, or in this block, or in this block. So these will contain references to other objects. Amidst all of this, how would the list recognize that these particular memory blocks contain elements that belong within that object? That is the specialized mechanic by which a linked list stores data. Let us see how that mechanism functions. Before we actually tackle that diagrammatically, let us take a look at the documentation for linked lists. So I will create an object just to gain access, import. There we go. And I do not need this anymore. I do not need this anymore. Now remember, with array lists, everything is stored contiguously depending on the sequential order. There are no gaps between the elements or the memory blocks. Thus, the array list is able to pinpoint or track the elements that comprise its contents because they are in a contiguous fashion. The array list knows the address of the first element and the address of the last element, which means that by default, everything in between also belongs within the array list. With linked lists, however, so with an array list, the memory block contains the element and only the element. With a linked list, however, it has the element stored within it, which is this one, E here, but as you can see, it stores two other elements by data type known as node. We will cover what that means in a moment. We will also cover why this is called first and this is called last. Though I prefer, let me see if I can find this one. You can also refer to them as last or first. we will cover why is it called first and last, and why it is also called, sorry, not first and last, I mean next, previous and next. We will see what those mean in a moment. So now that we know this, we can start tackling the structure or the functionality of a linked list. So now we know that the element by itself is not the only item stored within the memory block. There are two additional pieces of information stored alongside of it. However, we will ignore one of the nodes and just focus on a single node for now, before we tackle the scenario where we have both nodes active. So let us begin by adding the memory addresses of each of these memory blocks, because they will play an important role here. So let us say this is address 100, address 104. Now I am jumping by increments of 4 because the primitive data type int is worth 4 bytes in memory, if you recall, when we discussed it in the past. However, with reference data types, the sizes differ. We still have not discussed the size of reference data types yet, mainly because in my research I found conflicting, what is the word I am searching for? Conflicting results. So I am trying to track down the correct answer, but it seems that you cannot truly know the size of a reference data type. Some have stated that the reference data type has the same size as reference data types in C and C++, but they are not called reference data types there. They are called pointers in C and C++. 128. And that is what I am inclined or leaning towards, especially since the execution engine of Java is built upon C anyways, C and C++. So it would be logical to assume that it would adhere to the same memory sizes for variables. 1, 3, 6. There we go. Okay. What is the first element within the sequential order? It is 7. Okay, so we will start here. We will come to the recognition of 7 as the first element by the object at the very end. For now, let us understand what a node does, or what is the purpose of the node. Then we can return to this question later. How does the linked list know that 7 is the first element, especially if it is disorganized in such a manner? Here is what the node does. How does the list know, the linked list object know, that 1 is the upcoming element, or the element that follows 7? How does the linked list object know that 1 comes after 7, not before? Here is how. 7 is stored in its memory block, and 1 is stored at address 104. To link these two together, I need to know where 1 is stored and where 7 is stored. That way I can link these two together. So how do I bridge this gap? By using the node. What does the node perform? The node stored alongside 7 here will store the memory address of the next element, the element that follows 7. What is the next element after 7? It is 1. What is its memory address? It is 104. So this value will be stored in the node that is stored alongside 7 here. So if we create a partition to indicate that 7 is not stored by itself, there is also another value stored. This is where the node will be assigned. And let us use this color. So the node will store the memory address of the upcoming element, which is 1. What is the memory address of 1? It is 104. So here 104 will be stored. And this is a reference data type. This will be a pointer. So let us draw the pointer arrow and have it point to 1 like so. This is how the linked list links the list. Pun intended, of course. So this is how the linked list bridges the gaps between discontiguous or uncontiguous memory blocks by utilizing the memory address of the next element or of the upcoming element. Thus, these elements could be scattered in a diaspora throughout the entirety of the memory, and the linked list would still be able to track every single element because of the node. So the node object is stored alongside the integer object within one memory block. So that is how data is stored in memory blocks belonging to linked list. We have the element and we have a single node stored within it. Okay, let us continue. What is the element after 1 or next in line? It is 3. Right here. What is the memory address of 3? It is 100. So what will be stored in the node belonging to this memory block here? 100. So let us create the partition to indicate that alongside the integer data type, which is this one, there is a node data type, this one right here. And here we will store the value of this memory address, 100. And we will use the same pointer to refer to that element. Like, this will cause overlap. So I will use a different color just to highlight the overlap, nothing more. There and there. So now we have linked 1 and 3 together through the node. I just remembered that stupidity in Metal Gear Solid 2 where he tells him, "Oh, did you say nerd? Ho 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 ho." Anyways, man, that was a stupid game. Now let us move to 3. What is the element after 3? It is 4. Where is 4 located? At this memory address here. So what will be stored in 3's node? The memory address of 4. So let us create the partition again. Like so, and add 112 here. Then let us create the pointer. I am alternating colors to avoid overlaps. Actually, it will overlap here, so I can use this color. It is a bit too bright, but at least it creates visible contrast, which is what I want. so that you can see where the nodes connect or point to. Now that these two have been connected, these two have been connected or linked, these two have been linked, now we have 4 and 9 left to connect before we finish the linked list. What is the upcoming element after 4? It is 9. Where is it stored? At address 136. What will be stored in the node belonging to this memory block here? This address. So we will create a partition, and in addition to the value 4, we will also store a node object whose value is this memory address, which is 136, like so. Then we will create another pointer. I will use this color again. Again, the differences in color do not highlight specialty, they highlight contrast, nothing more, to avoid having the same colors blend in together. Now we have successfully linked all the elements together. But as you can see, you must have a single node alongside the element stored within the memory block, which means that this memory block is missing a node. So we need to add a node for this element right here. The question is, what will be the memory address stored in this node here? Now that 9 is the end of the list. Remember, this is part of the collections framework, as in it is a dynamic collection. It increases dynamically. If you add more elements, it will accommodate that, and it will shrink once you start removing elements. So if I decide to add 2 more elements, let us say I decide to add 5, 8, and 6, and this was stored here, for example, then the value of the node will shift to 120. But then we will ask, what is the memory address stored with the node associated with 6? So the question here is, what will be the memory address stored at 9 here? Since nothing comes after 9, nothing is the memory address. And what do we refer to as nothing in reference data types? What is the value of 0 for reference data types? We have seen for primitive, it is false for Boolean and 0 for numerical values. What about reference data types? The 0 for reference data types, or nothingness, is null. That means nothing is stored in memory, like so. This is now a fully completed linked list. The question here is, would this list be considered a singly linked list or a doubly linked list? How can we identify whether a linked list is singly or doubly? If it has a single node, it is a singly linked list. If it has 2 nodes, it is a doubly linked list. What do these, what difference would having two nodes entail? What is the difference between having two nodes and a single node? Well, this brings us to the direction of this list. We have moved from 7 to 1, then from 1 to 3, then from 3 to 4, then from 4 to 9, in that particular direction. How do we know this? By the memory addresses. After 7 there is 1. After 1 there is 3. After 3 there is 4. After 4 there is 9. I am unable to return from 9 to 4, or from 4 to 3, or from 3 to 1, or from 1 to 7. I am unable to progress in that direction. Why? Because I do not have a node that stores the memory address of the previous element, at least in this example. I only have a node that stores the memory address of the next element. This means that the direction for this list is a unidirection, a single direction. From beginning to end. I cannot return from end to beginning. Thus, it is a single direction, or a one direction if you like puns, though that band is really dumb. Thus, it is called a singly linked list. Well, now that we know this, how can we create a doubly linked list? We will come to standard and circular at the very end because the differences are slight and almost trivial. Almost, not fully. Okay, so let us create another diagram for a doubly linked list. So what I will do is, well, actually, to save time and avoid wasting your time, pause the video if you wish to copy this example, because I will redesign or repurpose this diagram to accommodate a doubly linked list. So pause the video if you would like to take time to draw this, and then once you are ready, continue the video. So I will start with the doubly linked list now. I will erase this because we will need to change the directions later. In a singly linked list, I am able to move in a single direction from beginning to end, like so. What if I wish to return from 1 to 7? Here, as you can see, I am able to traverse from 7 to 1, but I am unable to return from 1 to 7. What change must I implement to apply such traversal? Well, we have seen that the node is responsible for storing the memory address of this next element or of the upcoming element. It can also be used to store the memory address of the previous element. However, a single node cannot store two memory addresses. Thus, we create another node. So we will create another partition here. And in this node, we will store the memory address of the element preceding 1. What is the element previous to 1? It is 7. Where is 7 stored? In memory address 1, 2, 8. This is also why the linked list is able to identify that 7 is the first element. How so? Nothing is preceding 7. Thus, you will not find a node that stores the memory address of 7, which is 128. That means nothing precedes 7. If an element preceded 7, that means the memory address of 7 will be stored in the next node. That is how a list is able to identify if an element is a first element or a last element, as we have seen with 9 here. That is also why this applies to the circular linked list, which we will come to in a moment, but this is why there are nodes that are called next and nodes that are called previous. So you are able to traverse backwards and forwards. And by the way, the linked list provided by the Java library is a doubly linked list. You can design your own singly linked list if you want, but the one provided for you by Java is a doubly linked list by default. Instead of using purple, I will use orange to indicate that the address here is of the previous element, which is 128. That is the address of the previous element. So now let us draw another pointer. For the reverse direction, I'll probably add the pointers at the top here to avoid convoluting this diagram any further. But I will also use different colors for contrast. So the arrows drawn above here will refer to the reverse direction from 9 to 7. I'll probably need to lower this ever so slightly. There we go, because I will most likely need the space up here. So now we went from 7 to 1 in a singly linked list with this arrow here, but with a doubly linked list we were able to return from 1 to 7. So now we can press the next key to move from 7 to 1 and press the previous key to move from 1 to 7. We will apply the exact same principle for every other element. So for this arrow, we move from 1 to 3. How can we move from 3 to 1? Exactly the same. We will add the previous node here, and then we will store the memory address of the previous element, which is 104. Then draw the arrow and I am using different colors for contrast, nothing more. There we go. And as agreed, the arrows above indicate the reverse direction. So now we have connected 1 to 3, but also 3 to 1. 3 to 1. Now let us move to the next set, which is 3 to 4. We have connected it successfully here through a singly linked list. Now using a doubly linked list, let us connect 4 to 3, so in the reverse direction. So here we have 4. Since this is a doubly linked list, it must contain 2 nodes instead of 1. So we will add the partition to indicate that this memory block is storing 3 items, a next node, the element itself and the previous node. What is the memory address to the preceding element, which is 3 in this scenario? The memory address is 100. So we will put this here like so. And use brown. Let us use brown. Oh, for goodness sake, man. There we go. There. And then here. So now we have ventured from 4 back to 3 by using a node that stores the memory address of the previous element. Finally, we arrive at 4 and 9. We have connected 4 and 9 in the singly direction. Now let us connect them in the doubly direction, which is from 9 back to 4. What will be stored alongside the next node and the element 9? It will store the previous node. What is the memory address of the previous element? It is 112, so that is what will be stored here. And then we have the last arrow. Let us use pink. Hopefully it is not too bright. Oh man, that is an ugly color. And here, like so. Okay, sorry, I will be right back. Apologies for that, I have returned, and it seems that I will not have time to discuss standard and circular, so I will end with the last element for the day, or the last topic of the day, which is the previous node for the first element. Then we will discuss the differences between standard and circular in the next video, God willing. It will not be a lengthy video because the differences are incredibly simple. Now lastly, we have the first element, which is 7. As with the last element here, what is the element previous to 7, or what is the element preceding 7? Remember, in a doubly linked list, each memory block must contain 2 nodes. Must. So this is not an exception. What is the element preceding 7 here? Nothing. So the memory address is nothing, because nothing precedes 7, thus nothing is stored in memory preceding 7, which equates to null in the case of reference data types. And as you can see, node is a reference data type because it is a capital letter, and it is not any of the primitive data types. So the memory address in the previous node for 7 will be null. And that is it. That is the difference between a singly linked list and a doubly linked list. Now this list can traverse in both directions. So a singly linked list is unidirectional. Let me write it here for you. A singly linked list is unidirectional, whereas a doubly linked list is bidirectional. So you are able to traverse both directions in doubly, but in a single direction for the singly linked list. So is this a standard linked list or a circular? Maybe I will have time. Let us cover the differences between a standard and a circular linked list. The way I try to imagine a standard and a circular linked list is how you can visualize DNA in cells. The human DNA, and I am referring to the structure, not the arrangement, as in I am excluding how DNA wraps around the histone proteins and then a scaffold protein cements the two together to form a nucleosome, and then multiple nucleosomes connect together to form a chromosome. I am not referring to the arrangement. I am referring to the structure of the DNA itself. If it is unwound from the chromosome and placed in a single straight line, you would have meters long of DNA, and that is the miracles of God in His creation. That I believe, what was it, 1 meter long or 2 meters long, the DNA in one cell. So how is a 1 meter long condensed to microscopic levels? Subhanallah. And yet people do not believe anyways. So the standard linked list is similar to the DNA that is unwrapped and straightened out. Here we have the beginning of the list, which is 7. I will enlarge the font. 7. And here we have the end of the list, 9. If we would look at this in a practical example, the perfect example would be a playlist on your phone or a playlist on a media player on your computer. Let us say I have a playlist that contains all the chapters of the Quran, which is a total of 114 chapters. Once I reach the end, the last chapter, 114, after it finishes, the playlist will stop. It will no longer play. You will have to manually play the first chapter again. It will not loop automatically for you. As in, it will not traverse from the last element to immediately to the first element. Why is that? If you look at the memory address stored here, null, unless it is of course expanded, that is a different story. But the last element will always contain null as the value for its next node. Whether it is singly or doubly, it does not matter. This means that you are unable to traverse quickly from the last element to the first element. The same applies in a doubly linked list here, null. If you are on your playlist and I reach chapter 114 in the Quranic playlist, and here you have the two buttons, this is next and this is previous. If I press this one in a doubly linked list, it will shift to chapter 113. If I press this one, it will not transform to chapter 1. Why is that? Because the memory address here is null. The same applies to if this was chapter 1 here. If I press the next button, it will shift to 2. But if I press this button, nothing will happen. Why? It will not give me 114. Why is that? Because the memory address here is null. So you are unable to loop or to form a connection between the last element and the first element. This is a standard linked list. You may ask, well, why would you want that? That depends on the design. If you wish to design a playlist that does not loop back to the beginning once it finishes, then you would use a standard linked list. Well, what if I am designing a playlist that loops automatically once it reaches the last element and finishes the last chapter? It loops back to the first chapter of the playlist or the first song. That is where the circular linked list plays a role. So here I will design it as a circle, and how I envision this is the same representation as bacterial DNA, which is a circular closed loop like so, and it is a single strand. That is it. So if I wish to add the elements of the list here, we will add them like so. 7 and then 3, then 1 then 3. I will move you know what, I'll just delete it. 1, 3, 4, and 9, like so. Remember, in a standard linked list, you are able to traverse backwards and forwards. But let me just draw these to show you. You are able to traverse from 7 to 1, then from 1 to 3, then from 3 to 4, and then from 4 to 9. That is a singly linked list. In a doubly linked list, you are able to traverse from 9 to 4, 4 to 3, 3 to 1, and 1 to 7. The issue is traversing immediately from 7 to 9 and from 9 to 7, from the first element to the last element and vice versa or vice versa. This is the issue that we need to resolve. That is where the circular linked list plays a role. Here you can move from 7 to 1. This is of course a visual representation, nothing more. It is an illustration. From 1 to 3, from 3 to 4, from 4 to 9. You can also traverse from 9 to 4 if it is a doubly linked list, from 4 to 3, from 3 to 1, and from 1 to 7. This is also the solution to the dilemma of the playlist that we have presented here. Here I have the previous button in a playlist or in a music player, MP3 player, any type of player. And here I reached the last chapter of the Quran in the playlist, which is here. If I press next, if I press previous in a doubly linked list, it will move me back to the previous element, which is 113. But now, if I press next, something will happen, which is this, from 9 to 7. So it will move me back to the first element of the playlist. Similarly, in a doubly linked list, if I press forward here, it will move me from the first element to the next element, which is chapter 2 in the Quran. But if I press back, something will happen, which is this movement here, or this traversal here, from 7 to 9, so it will yield 114. So basically, if you wish to design a looping playlist, you would use a linked list. If you wish to design a playlist that does not loop, you can use a standard linked list or an array list. So this linked list can be used to loop back from 9 to 7 and from 7 to 9. Now the question here is, will we need to make changes to the last element's next node and the first element's previous node? Absolutely. What will be the changes then? So what I will do is I will copy this diagram. Do I even have space? I do not have space. Okay, I'll change it here then. So how do I link 7 to 9 and 9 to 7 like so immediately and directly? Pause the video, try to contemplate the answer before continuing. The answer is simple. For a circular linked list, instead of having null here, where the list ends, let us connect 9 and 7 together. So instead of null, we will place the memory address of the first element as the value of the next node. So I will use a completely different color this time. What is the first element's memory address? It is 128. Oh, I need to reduce the font to 8, like so. So now I have linked 9 to 7. How do I link 7 to 9? This, of course, if you are designing a singly linked list, let us pretend this does not exist. This is how you would create a circular singly linked list. For a doubly circular linked list, you will also need to change the previous node for the first element to match the memory address of the last element. So instead of null here, we will put the memory address of the last element, which is 136 here. 136. And this is how you connect the first element to the last element in a circular linked list, whether it is doubly or singly. If it is doubly, this will not be null and this will not be null. In a singly, you will not have the previous nodes, of course. This, however, will not be null. It will point to the first element, and that is it. In a doubly linked list, this will point to the memory address of the first element, and this will point to the memory address of the last element. Let me connect these using specialized arrows. I am running out of colors, for goodness sake. I will use black. So here, the black indicate the circular linked list. And this is actually the reverse direction, so it should be up here. This is the right direction. Oh wait, sorry. This is in this direction, so from 7 to 9 is considered in this direction from 7 to 1. So this is correct. I was on the right side. Okay. This is bothering me. There we go. And from 7 to 9 is the same direction as from 9 to 4, so it will be on the upper half here. Here, 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 like so. And those are the differences between a singly and a doubly linked list and standard and circular linked lists. By default, what is provided for you by Java is a doubly circular linked list. You have the next and the previous nodes, and you have the first and last nodes to point or loop or close the circuit between the first element and the last element, like so. In the upcoming videos, bi'idhnillah and God willing, we will check the different methods contained within the linked list class. Most of them will be the same as the array list. Besides, linked lists are not commonly used as opposed to array lists, but they are used. Whether or not they are commonly used, it is irrelevant. They are used. As opposed to, for example, vectors or enumerations, those are not used anymore at least. So we will cover the examples for, we will cover the methods belonging to the linked list class. I hope this video was helpful and beneficial to you all. Enjoy the rest of your day, everyone. Be safe, take care, and peace be upon you all. Wassalamu alaikum wa rahmatullahi wa barakatuh. Allahumma salli ala Muhammad wa ala ali Muhammad kama sallaita ala Ibrahim wa ala ali Ibrahim wa barik ala Muhammad wa ala ali Muhammad kama barakta ala Ibrahim wa ala ali Ibrahim fil alamin innaka hamidun majid.